All right, so we left off somewhere around here, and we said we were going to find what the electrophiles were that we needed to do to make the compound in B using the acetic ester synthesis. So I'm just going to delete some of the work that I had here for this problem. So just give me a second to get rid of that. And we'll just put this up here. All right, so what are we going to need? Well, we're going to start out with ethyl acetoacetate. So we're going to put ethyl acetoacetate. Our first step is going to be to treat it with sodium methoxide and ethanol. Then our first electrophile is going to be benzyl bromide or benzyl iodide. There we go, we'll pick benzyl bromide. Then we're going to do the same thing again, treat it with sodium methoxide again in ethanol. And we're going to add our second electrophile, which will be ethyl iodide or ethyl bromide or ethyl chloride. And then in the last step, we're going to treat that with water, aqueous acid, and heat that up. And that is going to give us a final product, just like that. All right, any questions about that one? Did everybody else get something like that? Thumbs up if you got those two electrophiles. Anybody get those two electrophiles? All right, cool. Yeah, so what you had to come up with was the benzyl bromide and the ethyl iodide, right? Those are the two electrophiles that are required to make that product. All right, good. So let's move on to section 21.6. Let's get some really neat connections in it. And if you remember that when we have an alpha beta unsaturated carbonyl, we made that from an aldol condensation. So you use sodium hydroxide and heat to do that. And if we just use sodium hydroxide, then we get the aldol addition product. But anyhow, if you take an alpha beta unsaturated ketone or aldehyde and you draw all of the resonance contributors, so draw all three resonance contributors that you get, you'll notice that in two of them, we have a positive charge. And on the first one, it has the positive charge on the carbon of the carbonyl. But on the second one, you have the positive charge on the beta carbons. You have two electrophilic positions in an alpha beta unsaturated ketone, right? You have the carbonyl carbon shown right here. This is an electrophilic position, but also the beta carbon is also electrophilic. And whether the carbonyl carbon or the beta carbon is going to undergo a nucleophilic attack, well, that's going to depend on the type of nucleophile that's used. So let's take a look at this. And it just so turns out that if you take an alpha beta unsaturated ketone, like we have here, and you treat that with a Grignard reagent, well, what it does is it reacts at the carbonyl carbon. And we call that 1,2 addition, and you can imagine why. If you call this atom 1 and this atom 2, you add an R group to atom 1, and then you add a hydrogen to atom 2, like that. So they're next to each other. So we call that 1,2 addition. But if you try something similar with a Gilman reagent instead, so if you remember the cuprate, we call that a Gilman reagent or a cuprate. Either one is totally fine. If you treat that with a cuprate, what it does is it adds the beta carbon. So we call that 1,4 addition. And the way you can imagine that is 1, 2, 3, 4, right? You end up adding an R group to atom number 1. And if you're like, well, there's nothing added to atom number 4, well, hold on. That's because we haven't looked at the entire mechanism yet. So we're going to get into that and explain a little bit or give a little bit more background as to why we call that 1,4 or conjugate addition. Okay, 1,4 and conjugate addition, they mean the same thing. And the reason we call it conjugate addition, right, because we know that this system here, where we have double, single, double, we know this is conjugated. And so you're adding at the two ends of the conjugated system. So that's why we call it conjugate addition, or you can call it 1,4 addition. I'll probably use both terms depending on the situation. So here's the general mechanism. And this reveals as to why we can call it 1,4 addition, right? If we count atom 1, 2, 3, 4, you can see that we're adding the nucleophile to the first atom, and we're adding the proton to the second carbon to produce an enol. But we know that enols are not stable and they undergo tautomerization. And in this case, this enol is going to undergo tautomerization to give us an aldehyde. So it looks like 1,2, but in fact, it actually is 1,4 addition. All right, so conjugate addition is in fact 1,4, but after tautomerization, it appears to be a 1,2 addition. But we don't consider the tautomerization as part of that conjugate addition. So going back, if we think about things like Grignards, stronger nucleophiles, so Grignards, A Grignard is going to do a 1,2 addition, whereas a less reactive nucleophile, like a Gilman reagent, is going to do a 1,4 addition or a conjugate addition. And it says here, if you make a typical enolate, like let's say you had some kind of enolate, like, I don't know, let's just pick something really straightforward like this maybe. If you had, I don't know, this kind of enolate, okay, that is going to give you a mixture of 1,2 and 1,4 addition product. So that's not really helpful. Mixtures are not a good thing in organic chemistry, right? We want to try to avoid that. But it turns out that if you have a stabilized enolate, well, that gives you 1,4 addition only. All right. And why do we call this a stabilized enolate? Right. The reason is because we can show the delocalization of the negative charge on this carbon and these two oxygens, right? So we get an extra resonance structure, whereas here we could only show it in 2 places. So stabilized enolates give conjugate addition or 1,4 addition exclusively. So what's going to happen is your nucleophile, the enolate, is going to attack at the beta carbon. You're going to end up doing a proton transfer to make the enol, and that's going to undergo a tautomerization to give you this aldehyde. So that's 1,4 addition. So look, we have 1, 2, 3, 4, 5. So we have a 1,5 dicarbonyl compound that we've formed here. So conjugate addition or 1,4 addition, you probably heard me say this before, we call that Michael addition. Okay, so Michael addition or the Michael reaction. And the nucleophile, we call that the Michael donor. So a Michael donor is a nucleophile, and a Michael acceptor, that's our alpha beta unsaturated carbonyl, which is obviously our electrophile, right? It's the electron acceptor. Okay, so our Michael acceptor is going to look like this. We're going to have a carbonyl, and then we're going to have an alpha beta unsaturation, right? So there's going to be some kind of group here and some kind of group here. All right, so there you go. Michael addition. Michael donor is our nucleophile. Michael acceptor is our electrophile. So here's a great summary of common Michael donors and Michael acceptors. And what do you notice about all the Michael donors, except for the cuprate, except for the Gilman reagent, which is shown here? All of them have, a scenario where you can draw a double stabilization or 2 more resonance structures where you can move that negative charge around. Okay, and I'm not going to draw it for all of them, right? But you can imagine for this one, you could draw a resonance structure over on this side. Oops, or you could put it over on this side. And even with the nitrile and the nitro, you should be able to draw those resonance contributors as well. I'm not going to do that right now. But if you look at all of the Michael acceptors, they're all alpha beta unsaturated carbonyls. So we have aldehyde, ester, ketone, amide. And then we have an alpha beta unsaturated nitrile here and an alpha beta unsaturated nitro. So any one of those would make a good Michael acceptor. So our Michael donors and our Michael acceptors, you should at least familiarize yourself with this table because we're going to see many of these Michael donors and Michael acceptors. All right. Anyhow, so let's keep moving here. And it says predict the major product of the following 3 steps, right? Give me 3 steps. Leonard Skinner, right? And show a mechanism for its formation. So I don't know if there's enough room to tackle the whole thing on here, but we'll give it the old college try. So what's going to happen in the first step is our hydroxide is our base, and it's going to pull a proton off. So we're going to rip off this proton like this, and we're going to make our doubly stabilized enolate. I'll go this way. So this is going to be our Michael donor. And then we have our Michael acceptor. So let me just draw the Michael acceptor like this. And so we're going to get a nucleophilic attack here. We form the double bond here. So there's our conjugate addition. And then our intermediate is going to look a little something like this. Okay, so we're going to have 1, 2, let's see here. Yep, there we go. And then we're going to have our negative charge out here. And we're going to have our cyclohexyl over here. Not my best artwork, but it will work for now. So that's done. So there's our conjugate addition. And now we're going to do our proton transfer. We're going to treat this with hydronium. And we're going to protonate the alkoxides. We're going to protonate this. And that's going to give us the enol form. So we end up with this. So 1, 2, there, like this, like that. All right. Am I missing a carbon? I am missing a carbon. 1, 2, 3. 1, 2. 2, 3. I'm missing a carbon, aren't I? Okay, let me go back and fix this structure. I'm going to go back here. I told you it was about counting your carbons correctly. So let's fix that. So I'm going to have what? I'm going to have 1, 2. So there's the first 2 carbons. There we go. That's a lot better. It's going to look something like that. Okay, I knew I was missing a carbon. Something looked a little funky there. Good. Okay, so in the next step, we're going to protonate that with hydronium. That's a lot better. All right, so we do our proton transfer, which looks like this. We're going to draw our enol. Enol is going to look like this. So we have 1, 2. There we go. So there's the enol. And just in the interest of time, I'm not going to draw the tautomerization mechanism. So this is going to undergo tautomerization. And so I'll just put here tautomerization. And that's going to give us the final product, which is going to look just like this. So again, 1, 2. There we go. Man, I'm still running out of room here. Jeepers. Let me fix this. There we go. There. So I'll just put an arrow like this and I'll put tautomerization, okay, which is a couple of curved arrows. There we go. All right. So again, we have a 1,5 dicarbonyl. So 1, 2, 3, 4, 5. So a 1,5 dicarbonyl is formed in the Michael addition. So again, this is a Michael or conjugate addition reaction. All right. There we go. Let's try another one, and I'll try to count my carbons more correctly this time. It says using diethylmalonate as your starting material and any other reagents of your choice, show how you would prepare each of the following compounds. So if you remember diethylmalonate, that was this guy. So if we just pencil in the structure of diethylmalonate, it was this diethyl ester. All right. And then after the whole sequence, you end up with some kind of derivative of acetic acid. Right, so you'd end up with some kind of derivative of acetic acid, and of course this would be some other kind of R group. And so if we look at this molecule that they want us to make, we know that this, let me use my red pen. We know that this part of the molecule, is coming from the diethylmalonate, right? That part's coming from the diethylmalonate. And so what we need to do is we need to add this part here, okay? And you might think, well, I could take my diethylmalonate, so I guess I can zoom out now. You might think, well, I'll take my diethylmalonate, okay, and I'll do a deprotonation on it using sodium methoxide, and that would give me this, right? That would give me the doubly stabilized enolate. And then could I treat it with this? So if I want to add this portion, could I use this alkyl iodide? Could anybody answer this? Could I do this reaction with the, could I do an SN2 like this? No, thanks, Audrey. Absolutely not, right? So somebody says tertiary, so probably not. That, right? You could file that under bad ideas, right? So this is not going to work. So we'll just think Audrey said no. I'm going to scribble a big red X over that. So a better option, right, Audrey, would be to do a conjugate addition because we know we can do that. So what if we had our electrophile as being this? So what if we had something that looks like this? Right? And then we put a double bond here. Could we do it then? Yes, this would be a Michael reaction. Michael donor, Michael acceptor. Wunderbar, right? There's nothing wrong with that whatsoever. And so that would be the best choice. So what our mechanism would look like, or what our reaction sequence would look like, is we would start it with diethylmalonate. So we'll draw diethylmalonate, and we would treat that with sodium methoxide. All right, and then we would put in our Michael acceptor, which would be this compound. This is our alpha beta unsaturated ketone. All right, so that would do our Michael addition. And then we would do a proton transfer at the end. So, and then we would heat it up in water, in aqueous acid, I mean. So aqueous acid and heat. And then that is going to give us the desired product. So we're going to end up with our product like this. And we could draw the intermediate that's formed along the way. So maybe I'll leave this part out and we'll just draw the product of the Michael addition, which is going to look like this. So let me count my carbons more carefully this time. So I have 1, 2, 3. So 1, 2, 3. Then I have my carbonyl here like this. There we go. And then there we go. And then I'm going to treat that with, what am I missing here? Oh, that's right. And then I'm going to treat that with aqueous acid and heat it up. And that's going to give me my final product. All right, there we go. I think I'm trying to make this more complicated than it needs to be. All right, so let's remind ourselves that the reason we crossed this out, I'll just kind of scribble it up here, is cannot do SN2 with secondary or tertiary halides, alkyl halides. All right, give me a thumbs up if you follow me on that, a Michael addition using diethylmalonate, and then we cook it up in acid and we make an we make a acetic acid derivative. Great. All right. There we go. So a little bit of conjugate addition. Now let me show you some variations on conjugate addition. And this first one is called the storic-enamine synthesis. It's a pretty cool reaction. I think it's one of the neatest reactions we see in this whole class. And again, it says because a singly stabilized enolate doesn't give a high yielding Michael reaction, Gilbert Stork, who is from Columbia University, made up this synthesis using an enamine. And do you guys remember we covered enamines in chapter 19? Enamine, anyhow. So if you don't remember, what we did is we started with a ketone, and then you could treat it with ammonia. Sorry, my mistake. You could treat it with a secondary amine, and that would give you an enamine. So maybe I should write that down here. Secondary amine, and that gives you an enamine. All right. And I know you know where I'm going with this, right? So if you had an alpha beta unsaturated carbonyl like this, you can see how this is going to react like that, right? It could be a Michael donor is essentially what they're getting at. So let's take a look here. And the reason why I'm sure you connected these dots already is because if you look at an enolate and you look at an enamine, you can see how they're both nucleophilic, but the enamine is actually less nucleophilic. Why? Because overall, right, the enolate has a charge of -1, but this has a charge of 0, right? The positive and the negative balance each other out. And so the enamine is less nucleophilic, and so it's more prone to be a Michael donor, to attack at the beta carbon. So what would be the point of all this? Well, after you do your Michael reaction, you end up producing an iminium ion. So if you look here, we have an iminium, and then here we have an enolate. But what happens is, and the book doesn't even cover the mechanisms, which I'm sure you could figure out, but all you have to do is treat it with aqueous acid, and you convert the iminium, gets converted into a carbonyl, and the enolate undergoes proton transfer to form an enol, and then tautomerization to give you a carbonyl. So you end up driving both of them to the carbonyl. So you end up with a 1, 2, 3, 4, 5. So you end up with a 1,5 dicarbonyl. So pretty cool synthesis, the Stork enamine synthesis. So here's the whole kit and caboodle. Okay, Stork enamine synthesis. You start out with cyclohexanone, then you treat it with a secondary amine. Now I just looked in my notes this morning, and the secondary amine that we use most of the time in our textbook is dimethylamine. So that's 2 methyl groups, and then the nitrogen and a hydrogen, right? That's the same thing as CH3, NHCH3. That's the one our textbook chooses most of the time. So it's the one I'll usually pick too. And then a catalytic amount of acid, you drive water off, you make the enamine, and then it does the Michael reaction with your Michael acceptor, and then you hydrolyze the iminium and the enolate both to the carbonyl. So you end up with a 1,5 dicarbonyl. So again, if we count 1, 2, 3, 4, 5. So we make a 1,5-dicarbonyl. Now, something I want you to write down if you're making notes is that the carbon-carbon bond is formed between carbon 2 and carbon 3. Okay, so the bond that we formed is here between carbon 2 and carbon 3, and I want you to keep that in mind as we work forward. It's just something I've kind of, learned to mention to my students over the past couple of years. It makes things a little bit easier when you're trying to solve problems where we look at conjugate addition and doing the storic enamine synthesis. So that brings us to this problem, okay? It says, using a storic enamine synthesis, show how you might go about doing the following transformation. So we're starting out with acetophenone, that's this compound here, and then we want to make this 1,5-dicarbonyl. So 1, 2, 3, 4, 5. All right, so we can see that the acetophenone is bringing all of these carbons. So let me just circle them here. So everything up to carbon 2, right? Because you make the bond between carbon 2 and carbon 3. So if we think in terms of our retrosynthesis, the green part is going to come from this. So the double bond is going to be between carbons 3 and 4. So this is kind of one of Mr. Dion's sort of shortcut methods. So that's going to be your Michael acceptor, right? And you know that if you're making a 1,5-dicarbonyl, you can't make an enolate. That's not a Michael donor. You have to make an enamine. So that's going to be the first step, right? Is to make the enamine of acetophenone. And so if I can just, write down the steps here, maybe I should switch over to a blank document here. Just give me a little Taylor Swift blank space here. So let's see if I just rewrite this. So this is, again, 21.38 A. So if we start with our acetophenone, and we're trying to make this 1,5-dicarbonyl, so we have our portion of the molecule that comes from our acetophenone. That's everything up to here. Then we have this bond, there we go, like this. So again, the way that I did the retrosynthesis is I said, well, this part is going to come from this Michael acceptor. Okay, so now all we need to do is take the starting material and make the enamine. So the way that we're going to do that is we're going to treat it with dimethylamine and a catalytic amount of acid. Then we write minus H2O, and that's just to show that we're driving off water. So we're going to draw the enamine that we form, which is going to be this enamine. And again, if you need to review that, that's in chapter 19, enamine chemistry. So we make our enamine, which is going to be a Michael donor. So this is our Michael donor. And then this is going to be our Michael acceptor. So I'll just copy and paste it down here. So this paste. So this is going to be our Michael acceptor. So let's just draw a little bit of curved arrows for this. So we're going to have our enamine acting as a nucleophile. It's not a strong nucleophile. And we end up with this. So let's draw the intermediate, which is going to have the iminium ion in it. So we'll draw that first. So we end up with a double bond here. So that means we have a positive charge on our nitrogen. Then we have, and you have to draw it with that sound effect, right? And then we have our enolate over here. And then again, you don't have to include any mechanism for this. Just treat it with aqueous acid, and that's going to hydrolyze the iminium to the ketone, and that's going to protonate the enolate to the enol, and that's going to tautomerize an acid to give you the dicarbon or the carbonyl. So it's a double whammy. It's two reactions in one kind of thing. Can we try one more before we move on to Robinson? Give me a vote. Anybody thumbs up if you want to try one more? I think we should. Okay, somebody else wants to try. I'll go with it. So this is 21.38B. So let's just practice these disconnections again. 21.38B. Let's just give it the old college try. So we've got, this is 3-pentanone, and we're trying to make this interesting compound here. Okay, and I'm going to draw it a little bit different than they do in the book, just so I can help you with the disconnections. I'm going to color code it here. And so that kind of shows you that, maybe a better way to draw this ketone would be to draw it like this, right? Because that's what we're going to make our Michael donor from. And our Michael acceptor is going to be this alpha beta ketone. So it's going to be the alpha beta unsaturated ketone of cyclohexanone. Give me a thumbs up if this makes sense, this disconnection that I've done. Or stop. Does anybody have a question about this? I want to make sure we're kind of on the same page before we, train kept it rolling sort of thing. Okay, so let's do the enamine. So we're going to take dimethylamine, catalytic amount of acid, loss of H2O, and we're going to make the enamine, which looks like this. Okay, and again, we usually make it from dimethylamine, and then we're going to treat that with our Michael acceptor, which is going to be the alpha beta unsaturated ketone here. Yep. All right, then we're going to do our Michael addition, zoink, which looks like this whole holy host of arrows there, right? So we end up with, oops, that's not pretty. We end up with something that looks like this. So we have our iminium ion here. There's that part of the, oops. I'll use my blue pen here. And then we have this. Oops, I put my double bond in the wrong spot. My mistake. Let me move it. There we go. There. Nope, still ugly. There we go. That's a lot better. So we have our enolate here. And then we're going to treat that with aqueous acid. And walla walla bing bang. We hydrolyze the iminium. We protonate the enolate to the enol. It tautomerizes. And we get a 1,5-dicarbonyl. And again, you can count. So we have 1, 2, 3, 4, 5. And at the very end of the textbook, or at the end of this chapter, it's kind of got this little blurb about counting, the distance between carbonyls and what strategy you would use. So don't worry, there's a neat little summary about this at the end of the chapter, and we'll take a look at that in just a few minutes. So where were we? Somewhere down here, spawning off the coast of that salmon. All right, so let's move down to this one here. Where were we? We're way down at the end. Da, 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 da. All right, covered all this. Covered stork. Gilbert stork. We covered that one. Checkaroo. So now we're on to Robinson annulation. Boy, do I remember learning this when I remember the day I learned this reaction, the Robinson annulation. You could call this would fall under the umbrella of what we call, and this term is not in our textbook, I don't think. This would fall under the umbrella of what they call tandem reactions. Reactions. Jeepers, Mr. Dion. Thinking about too many things at once. So tandem reactions means kind of like two reactions in one reaction flask, like happening at the same time. You do one, and then it sets it up to do another one. And one of my favorite books in the planet Earth, you've got like Bible, 1984, and then there's a book that I like, and the name of the book is Tandem Reactions. It's written by I think he's the author of it. But anyhow, this guy was amazing author. And just a book I really liked. I got into it when I was in graduate school. I haven't read it in a few years, but I really liked it. And so Robinson annulation, I remember the day that I heard about this reaction, I said, I want to do this. I wanted to do a reaction kind of like this. And I did work on some tandem reactions when I was a graduate student. But it's a really cool reaction because all you do is mix two reagents. You put a stabilized or a 1,3-dicarbonyl, which can make a stabilized enolate, and a Michael acceptor together, but if they're the right length, right, so that you could form a 6-membered ring. What happens is it does a Michael addition reaction. So the Michael reaction, we've just been studying it for the past 45 minutes. And then you've got it set up so that if you make an enolate on this, you can end up doing an aldol condensation, right? So you end up with an alpha beta unsaturated ketone. So it's two reactions in one. And in case you're wondering, yes, you actually go directly from here to here. Okay, this is all done in one reaction flask. So all you have to do is just treat it with sodium hydroxide and heat it up. Is that cool or what? 2 reactions in 1 reaction flask. Wouldn't it be neat if you could do 10 reactions in a reaction flask? Anyhow, very, very cool chemistry. Give me a thumbs up if you follow me on the concept. Is everybody with me? First you do a Michael, then you do an aldehyde. Okay. I just want to make sure that somebody's with me since I can't see your faces. Anyhow, so the only thing about the Robinson annulation is it can be a little tricky to make the disconnection, right? So if I, like, let's say in your homework or something, it said make this compound, right? How do you go backwards in a Robinson annulation? Can I just show you how to do it quickly? So what you do first, if you had to do a retrosynthesis, is you would break this bond. Okay, so you break the alkene first, okay, and then you draw a carbonyl on this end, okay, the end that's not attached to the other carbonyl. So you make a carbonyl, and then from that you find the 1,3, right? 1, 2, 3, and then you break the bond between the alpha and the beta, and then that will give you your Michael acceptor. So that is kind of a short version of it, and you probably are going to have to try it yourself before you're like, yeah, I'm pretty confident that I could do a Robinson annulation. But that's the retrosynthesis that we want to do. So with that in mind, let's take a look at this question. So if you understood, or if you tried to follow along with what I just said, it will make the disconnection a lot easier. So they're telling you, make this compound using a Robinson annulation. So here's the Mr. Dion way to do it. We'll do our first retrosynthetic step. Remember I said we were going to break this bond, and we were going to put the carbonyl on the carbon that I have in red. So let's start by doing that. So that's going to give us this compound. So we're going to have a dialdehyde like this, okay? And then we're going to have, so I'm going to count from the carbon in the middle. We've got 1, 2, 3, 4, 5, right? So we've got 1, 2, 3, 4, 5, like that. So if I put the numbers here, we have 1, 2, 3, 4, 5. Did I add an extra carbon? Oh, I did one. One. No. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4. Let me try numbering it a different way. Let's number from the carbonyl. That might be easier. So what if we number like this? So if we count, I see, I'm missing this methyl group here. Oops. Son of a gun, I didn't mean to do that. There we go. There's my pencil. So there we go. So now we have something that looks like this. There we go. That looks a lot better, like that. Okay. So now if I count, you can see that from here I have 1, 2, 3, 4, 5, right? And I had 1, 2, 3, 4, 5. All right, had it right all along, just kind of drew it in a funny orientation. Okay, so now you can see that this is the 1,3-dicarbonyl here, right? So that means that this is our alpha carbon and this is the beta carbon. So this is where we make the second disconnection. So now if we go back another step, okay, what we're going to have is we're going to have this as our Michael donor, or once we deprotonate it, our Michael donor will be this, and our Michael acceptor is going to come from this part here. So our Michael acceptor is going to be this compound. All right, so those are the starting materials that we need to do the Robinson annulation. So give me a thumbs up if you follow me on the disconnection. I was kind of counting funky there for a second. But it was just the way I drew the bonds. I had it right at the beginning. I just drew it a little strange. So this is the answer to the question. That's what you need. Okay. So if you're wondering, well, how do I write it down? You literally write this. You put the 1,3-dicarbonyl. And then you're just going to say, well, I'm going to add the Michael acceptor, sodium hydroxide, cook it up, and that's it. And that's going to give you the product. And that's it, product. Okay, so this is my method of doing the disconnection. I think it's the best way of doing it. Somebody asked me this question in a job interview one time, and I was able to answer it, using this disconnection method. I didn't tell them that's what I was doing, but that's how I did it. So anyhow, hopefully you'll find that useful. when you're looking at, if you try another question that involves Robinson annulation. So before we take another break and get into some more synthesis problems, the end of this chapter, usually I just kind of gloss over the very end of these chapters where it says synthesis strategies, because this is the end of many of the chapters in this class, right? But there is one kind of nuance that they show you in this section, which is not a new reaction, but it just shows you how to put two reactions together. So I'll show it to you. Again, why is this such a great chapter? It's because most of the reactions in here form carbon-carbon bonds. And like I've told you many times, if you took organic one with me, you'll remember I always said, how do you get a Nobel Prize? Learn how to, or find a way to make carbon-carbon bonds in organic chemistry, and you'll get famous. So yeah, also oftentimes we made compounds that had two functional groups, like a ketone and a ester, or an ester and an alkene, right? Things like that. And so you need to know aldol reactions. You need to know aldol condensation, aldol addition, Claisen condensation, the Michael reaction, storic-enamine, all that stuff. And if you're wondering, well, how am I going to sort that out? Well, the positions of the functional groups in the target compound can give you some kind of clue as to what reaction you would need to synthesize it. So for example, if you're making a 1,5-dicarbonyl, you've got to do some kind of conjugate addition. And so a storic-enamine is a really good place to go if you're trying to make a 1,5-dicarbonyl. Whenever you have a 1,3, it says here difunctional. I learned bifunctional when I was a student. But anyhow, if you're trying to make some kind of 1,3 difunctional compound, ester, ketone, aldehyde, alcohol, that kind of thing, it's going to be either an aldol or a Claisen reaction, one or the other. You just have to figure out which one it's going to be. Obviously, this is an aldol addition. This is a Claisen condensation, right? And then, so this is kind of a new thing. So I'm going to put a red star. It's got nothing to do with mechanisms, but this slide shows you how to put two of the reactions together that we've learned. So it says we've learned two methods of alkylation. We learned one way to alkylate at an alpha position, and then we learned another way to alkylate at a beta position. And so the alpha position of an enolate attacks an alkyl halide, you know that. Then a Michael donor is going to attack the beta position. And so you can kind of mix the two. So if you take a cuprate, so remember, this is a Gilman or a cuprate, right? That's going to attack at the beta carbon. So maybe I'll color code this in blue. And then if you make that enolate, what's going to happen? So after the first reaction, there's not a lot of room on here, but what you're going to end up with is this intermediate. So the Gilman is going to attack, and you're going to end up with this guy where you have the ethyl group in here. Okay, so this is the intermediate that's formed after the first step. So then you can imagine that if you put it in the presence of methyl iodide, and again, I don't have a lot of room here, that what's going to happen is it's going to do an alkylation on the alpha carbon. Okay, so you add the methyl group to the alpha carbon. Give me a thumbs up if that makes some sense to you. So Gilman adds to the beta, you make an enolate, and then that just does an alpha addition, right, at the alpha position. Pretty cool reaction, huh? So it shows you a way to put something at the alpha carbon and the beta carbon simultaneously. So this is, in a way, this is kind of new because they didn't show you this during the chapter. It's only in the very end. So that's why I'm, kind of going over this stuff with you. All right, so this is a new reaction, and they like to ask this question. Okay, I think there's a couple questions in the homework, and it usually comes up in the quiz once or whatever. So let's just do a short review of the reactions because there are a bunch of them, right? There are a bunch of them, and it's not like the carboxylic acids chapter where a bunch of them are identical or very close. Okay, so the first one we learned was alpha halogenation of a ketone using a catalytic amount of acid and bromine. So we went over that in detail. Then we learned the HVZ reaction, or the Hell-Volhard-Zelinsky, and there's a variation on the Hell-Volhard-Zelinsky that's not shown in here. It's actually a variation on this reaction, really, but I'll go over it with you. And that is, we said that if you took a ketone, so I'll just use cyclohexanone as an example, and if you treat that with bromine in a catalytic amount of acid, so I'll just put H3O plus here, right? You do the alpha bromination, but then we said if you treat it with a base like pyridine or lithium carbonate, so I'll just put pyridine, right? We said that that was a way to make an alpha beta unsaturated ketone. So I just don't want you going back through your notes and saying, well, where's that reaction? Why isn't that in the summary? Because it's not shown in here. The next one was the haliform reaction. So we said you can take a methyl ketone. So remember, haliform reaction, you have to have a methyl ketone, and then you treat it with sodium hydroxide and bromine, chlorine, or iodine. And if you do it with bromine, of course, you would end up also forming bromoform, right? And we explained why you can lose CBr3 minus as a leaving group. It's possible. Then if it was CHCl3, it's chloroform. If it's CHI3, it's iodoform. So very cool reaction. The next one, we went over aldol addition and aldol condensation. Remember, the key difference between the two is heat. So aldol condensation, you just use sodium hydroxide and water. Aldol condensation, we use NaOH and heat, okay, to drive off water. Then we talked about a crossed aldol reaction. Then we also talked about directed aldol. So I'm going to scribble that down here because I don't think it's mentioned in here. So directed aldol, and that was using LDA. So we went over that. Then we talked about the intramolecular aldol condensation. So I think we went over that kind of towards the end of the last lecture. What did we cover after that? We did Claisen. So that's with esters. So Claisen is with esters. So we did Claisen condensation. And then we did a crossed Claisen. We also did directed Claisen. So using LDA, which isn't scribbled on here. We did the intramolecular Claisen, which is the Dieckmann cyclization. And that's something we looked at the very end of the last class. We actually started that today. We started kind of here and here today with the first couple of questions that we looked at. Then today we also covered alkylation. So we covered thermodynamic enolate, so thermodynamic, and then we covered kinetic enolates and how to make those. We went over the malonic ester synthesis, and that uses diethylmalonate. So that's this compound. So you have to know diethylmalonate. Then we did the acetoacetic ester synthesis, and this uses ethyl acetoacetate, kind of a long word. I guess you should kind of familiarize yourself with the name ethyl acetoacetate. So we went over that, how malonic ester makes a derivative of acetic acid, and the acetoacetic ester synthesis makes a derivative of acetone or propanone. Then we covered Michael reactions. So we said a cuprate will do conjugate addition and a stabilized enolate will do conjugate addition. Then we talked about how if you have just a carbonyl that's not stabilized or not a Gilman, you can make an enamine from it, and that will do a conjugate addition. It's got its own name. It's called the Stork reaction or the Stork enamine synthesis. It gives you another 1,5-dicarbonyl, like this one here did, okay? Then we covered the Robinson annulation, which is a Michael addition. So it's a Michael reaction followed by an aldol condensation reaction. And those are all of the reactions that we covered in this class. So I think we should take a short break before we come back and tackle this one. But I do want to kind of review it with you before we go on a break. So it says using cyclopentanone, so that's this carbonyl compound, as your starting material and any other reagents of your choice, propose an efficient synthesis for each of the following compounds. So you can see that if we color code the cyclopentanone in blue, for example, right, that this part of the molecule must be coming from our cyclopentanone, and then all of this spinach over here must be coming from something else. And so what is that something else going to be? So you're going to have to come up with some kind of synthesis for this one. So I'll let you think about that before we tackle it. And the next one, you can see that we've got, if this is our alpha carbon, this is our beta carbon, that we'd have to make some kind of connection here, right? So we're going to use a different strategy to make this compound. And I want you to think about this one pretty hard before you say, oh, I'm 100% sure I know what I'm doing here. And then I'll just show you, we're going to tackle these ones too, okay? So this is a problem where they get you to install an alkyl group at the beta carbon and the alpha carbon. So I want you to give that one a try. And this next one is also kind of interesting. But if you think about this as being your alpha and this is your beta, well, they are adding something at the alpha and beta. And of course, you can reduce the aldehyde down to the alcohol. You guys know how to do that. So I don't even have to tell you. So why don't we take a short break and then we'll come back and tackle these two problems.